Alright, now let's see the memory area in S7-1200. So we have this chart which shows different memory area and its description. Now first is process image input. As I told you before, we have a special memory allocated for the inputs. So let me take a pen. So this is the memory area dedicated to my inputs, which will read the status of inputs and it will store its status in the memory. Okay. So it also says the CPU copies the state of physical inputs to iMemory. iMemory is the input process memory at the beginning of the scan cycle. Okay. Then you have process image output. So this is for the outputs. So it will store the value of the outputs in another memory. Okay. The CPU copies the state of Q memory to the physical outputs at the beginning of scan cycle. So whatever value you have in the process image, it will be copied to the outputs. Okay, so what happened inside the PLC? First, your inputs are stored in a memory. Okay, now by this memory, this logic is solved. Okay, if this is true, this will be true, and the status of these outputs will store in another memory. I'm calling it as M2. Let this be M1. Okay, so this is coming from my switches. So switches give the information to this memory. Logic is solved. The output is stored in the output memory, and this gives the output to my output terminals, which will turn on the indicator in that case. Okay, so that's how the information is flowed. Physical input store the value in process image input. Logic is solved. The output status of this ladder logic output is stored in the memory, and this memory gives the status to the output terminals, which will actuate your outputs. Okay, then you have a bit memory. Now bit memory, we have some special memory in our PLC. One is a general bit memory, one is a specialized bit memory. Specialized bit memory has some special functions, which, for example, you have internal clocks in PLC, which will be on and off by its own interval. You can use this internal clocks in your logic. Okay, so this clock, if I say it's a special memory clock, this will be on and off by itself. Okay, so I can use that special memory in my logic. Okay, then you have a general memory, which is used for latching, for making some timer circuits. You can use some normal bit memories in that as well. We can see that in our programming lessons. Then you have temporary memory. Now what happens if you have a lot of input and outputs? PLC sometimes store the result in a stack. Okay, stack is it's a group of memory allocated for making the logic, for processing the information. Okay, so we call it as a local memory or a temporary memory. So it says it is used during the execution of the logic. Okay, when the logic execution of the code finishes, the CPU reallocates the local memory for execution of other code blocks. So this got cleared as well. So if stack is cleared, it can be used for another process of information. Okay, then you have a data block. Now suppose my input is actually connected to a sensor, and my sensor is used to read the number of blocks, number of boxes, number of bottles. So it could be anything, and I want to store that information in my PLC. I will use data blocks. Okay, data blocks is generally can be displayed in your HMI, in your touchscreen. Suppose here you can count how many bottles are coming, how many boxes are going, how many people are coming. So that information is stored in special memory, which is known as data block. Okay, so data block can be used in FBs or ladder logics. So it's generally read and write. You can also erase this memory. You can rewrite this memory, and this can be stored in, it says bits, bytes, words, or double word. Okay, it says you can use for timers and counters. For example, you want to change the time of your process, so that time value will be stored in a data block. All right, so these are the different memory areas. It's S7-1200. Okay, let's proceed to the next slide. Okay, now you have a fact which you should read. It's generally a fact which may help you in your logics. Now next is wiring the inputs and output. This is one of the main subject of this lesson, because many a time there are confusion how to wire the inputs, how to wire the outputs, because incorrect wiring or incorrect wiring of input and outputs may lead to some accidents as well. Okay, so starting with wiring the S7-1200, so we are using this model number. So this representation of wiring is of this model number. So you can check your PLC as well. The basic fundamentals are pretty same. So starting with, we have seen the line 1 and neutral. This is given line 1 and neutral from the power source, okay, to energize the PLC, to provide line and neutral, which will provide power to all the inputs and processor of the PLC. Okay, then you have 24 VDC output, which is LM, L plus and M. Okay, now this IM is the common of your inputs. I'll come to that later, but first let's understand this 24 VDC, as I told you, is converted from this AC. Okay, this AC is converted to DC by the power supply, which is already inside this PLC. Okay, so let me take a pointer. Yeah, so this converts into DC. So this DC is inside the PLC, which you can use for various purposes. So one of the purposes is to wire the inputs. Now how to wire the inputs? It says 24 VDC inputs. You have to check your digital input status, whether it's DC or AC. So in our case, it's DC inputs. Okay, if it is AC, its wiring will be different. So this is for DC inputs. It says 8 into 24 VDC, 6 milliampere per point. It means every input can only bear 6 milliamperes of current. It draws 6 milliamperes of current. Okay, so be careful with your inputs. So how to connect that? So if you see this 1M, now let me change my ink color. Now this 1M, this is the common of my PLC. Now what I have done is I have connected a wire from 5 to 6. Now this 4 wire this is in pink color. This is represented by 24 volts. Okay, I have written here. This is 24 volts L plus, but this M wire it's a 0 volt. So I will take a black color. This is 0 volt. Okay, so 0 volt is connected to my 6 number. So 6 number is having 0 volt. Okay, now what I have to provide to 7, 8, 9, 10 to turn on the input, it's the 24 volts. So we have to maintain a potential difference between the input terminals and the common terminal, which is IM. So this is common to all the inputs here. Okay, so if 0 volt is connected to IM, you have to connect 24 volts to other inputs to activate it. So if you see, a wire is coming from here and it's coming to the switch. So we have 8 switches. So this is similar to what we have in our PLC simulator. If I open up this for you, now if you can see here we have M. So this M is given 24 volts, and this 1, 2, 3, 4 it's getting 24 volts from my switches. That's why if I turn on the switch, my LED status goes on and off. Okay, so if I turn on the switch, that's how it's getting 24 volts and my status is getting on and off. Okay, so if you turn on this switch, this particular LED will be on. If you turn off this switch, this LED will goes off. This is how you connect the inputs. It's very simple. You just have to maintain a potential difference between your PLC and between your IM common terminal of PLC and your input terminals. That's how you connect the inputs. Very simple. Now coming to analog inputs. Now you might wonder why we use analog inputs. Digital is just for switches, on and off, or limit switch, or sensors, proximities. Now for analog input, you might know a device known as potentiometer. Okay, this is a potentiometer. We can also say it as pot. Now potentiometer is a variable resistance. Okay, when you move this wiper, its resistance changes. So it has a resistance rating written on the potentiometer. So let's assume it has 5 kilo ohm internal resistance of this, not internal, the resistance of this pot is 5 kilo ohm between this leg and this leg. This is 5 kilo ohm, but this middle leg will give you variable resistance. So this is from 0 to 5 kilo ohm. Okay, sorry for my bad handwriting, I'm using a mouse. So this is 0 to 5 kilo ohm. So what happens when you supply, if you see this wiring, what we are doing here is, this is a power supply, and generally it is 10 volt. Okay, 10 volt power supply, which supplies positive 10 from this positive terminal and 0 from this negative terminal. So 0 is connected to one part, one terminal, one leg of my potentiometer, and positive is connected to 3 terminal. Okay, this is a joint. So this 0 is also going to my 2M. 2M is the common of my analog input. 1M was the common of my digital input. So this is getting 0 volt. Now this 2 is having a variable resistance output. It means it is a voltage divider. It will give me variable output. So the voltage was 0 to 10 volt. In this potentiometer, it is given 10 volt. So the output from this leg will be 0 to 10 volt. Okay, from this potentiometer. So based on its position, if this is at extreme left position, I will get at this position, I will get 0 volt. At extreme right position, I will get 10 volts. If this is at middle position, I may get 5 volt. Okay, that's how you get the different voltage from this potentiometer, and that voltage is given to my 2 number pin terminal of my analog input. Now this is about wiring this potentiometer. What happens inside the PLC with this voltage? If this is at 0 volt, my PLC will have some digital bits. For example, it says resolution 2 into 10 bits. Okay, now what is a resolution? Resolution means the conversion rate of your PLC. Okay, 2 into 10 means each terminal has 10-bit resolution. 2 number has 10 bit, 3 number has 10 bit. So we have 2 inputs with 10-bit resolution. Now 10 bit is what? 2 raised to the power 10, which is 1024. Okay, so if my input is 0 volt, let me write the range. Let's write 3 ranges, 0, 5, 10 volt. So if my input is 0 volt, my conversion bit will be 0. If my input is 10 volt to my PLC, it will be 1023. But if my input is 5 volt in between, it will be approximately half of it. So if your wiper is somewhere in between, you will have proportional bits in your PLC. So this analog input will tell you the position of your wiper. You can make a logic and you can convert this digital range of bits into the angle or the position or whatever you want, how much deviation is there. You can calculate that in angles. So this is one of the examples how to use analog bits, analog inputs. Now we have relay outputs. Now in relay outputs, we have connected some lamps here. This is the indicator. This is the symbol of an indicator. Now what we have done, this is a relay output. 6 into relay output means we have 6 relay outputs. It says V 30 VDC or 250 VAC and A 2 ampere. VDC means you can connect digital outputs here of the range 30, and 250 VAC means you can connect AC output of this range, voltage range. And for each range, the current limit is 2 ampere per point. So 2 ampere each can be given by these outputs. So internal relay has ampere rating of 2 amperes, which is quite a decent rating. Okay, so how to connect that? Now you see that this is L1, this is the line. Line is connected to my pin number 1, which is IL. IL is my common, and 2L, pin number 6. So what happens when the logic inside the PLC is solved? Let me take another pen. Yeah, suppose you have a logic which says this first input, and then you have an output. Here I'll make an output which is connected to my I0.0, and this is connected to my input. Okay, so what happens if this input goes on? Its corresponding bit will be true inside the PLC. So this will be on, this output will be on, and suppose this is addressed with 0.0. So what happens? The common of this output, the line will travel from here to here because this is true. So line will come out, and this is now having a line here, and this is connected directly to my neutral. So this lamp will be on. Okay, that's how your output is wired to turn on by relating the inputs, the ladder logic, the ladder program inside. If you do not connect anything to pin number 1, it will be shorted here, but nothing will happen to the output. So whatever signal you give to pin number 1, which will come out from the outputs if inside the bit is on, corresponding address bit is on. Okay, I hope you understand that. Similarly, if I have connected line to pin number 6, if my output 4 is on, so this line will travel to the 7. If 5 is on, this line will travel to the 8. if 4 is on, this 0.2 is on, this line will travel here. So the signal you provide to pin number 1 will come out to 2, 3, 4 and 5 only, not 7 and 8, because this is dependent upon 6. So this one common has 4 output contacts, this common has 2 contacts. So you can also have 4 AC outputs and 2 DC outputs by providing DC here. It's not always necessary to short 1 and 6. If you have 2 DC outputs, you can connect DC to 6 number and AC to 1 number. That's how you can change the input and outputs. Okay. Then you have Profinet LAN Ethernet port to connect to your PC for programming. So this fact says you have an inbuilt power supply which converts AC voltage to DC voltage. Okay. So let me clear